Okay. We're recording now. Thank you for reminding me. Okay, so just for the purpose of the recording, this lecture, we're talking about 3 different styles of distributed architectures. And we were right in the middle of talking about pipeline architectures. We have like the different components are called filters. They're possibly, these are objects, think of them as objects, possibly in different programs running on different machines connected by a network. They communicate by stuffing messages into an output pipe, and then the next guy reads the message from the input pipe. Yeah, so so somebody's asking if the different sections, lectures recorded. No, sorry about that. It's only the 12 o'clock that I record, because I always think, oh, well, I get all of the bugs out, in the 10:30. You guys are the lucky ones. So this is the only one that I bother recording. And so then let's see, here was the class diagram that we talked about. And then here was a sequence diagram showing a data-driven pipeline, just one message working its way through a data-driven pipeline. Demand-driven pipeline would start at the consumer's end, where we're demanding data, and then wakes up the producer eventually. We're waking up filters here we're imagining some form of publisher-subscriber pattern to wake them up and know that they have to get busy and do some work for us. Again, something that's important, I'll repeat it again. These filters are not aware of each other. They're only aware of their input pipe and output pipe. So you can mix and match these things. So here's some applications of them. So really, computer science has some interesting precursors to it that influence computer science. And one of those was signal processing systems. Signal processing systems have been around for a while. And signal processing systems have championed pipeline architecture. So here's like a kind of a little toy signal processing pipeline. We have like a source for signal. This could be like an electric guitar in a recording studio, or it could be like a radio signal from some space aliens in deep space somewhere. And so these signals are coming in, and maybe you would have like a noise filter. So some of it's signal and some of it's static, for example, or pops or hums or things like that that have to be filtered out. So this would be like our tester, right? Is the signal valid signal or not? Okay, and then maybe like the next stage would be an amplifier, which makes the signal louder. Maybe the consumer here, so the amplifier would be a transformer. It takes a quiet signal this and turns it into a noisy signal. And then the recorder's the consumer, which is just, putting the signal onto maybe tape or some other medium. So that's basically what's going on in your recording signal studio. And that's also what's going on, like if you're using some software like Fruity Loops or something like that, which is essentially like a virtual recording studio, GarageBand maybe. You are basically building a little pipelines like this. You have lots of different kinds of signal processing elements that you can use to build your pipeline. In fact, there is a project associated with pipeline architecture, which I'm not assigning to you this semester, but sometimes I assign it, which you build like something like GarageBand, so that you build your own little. It's a kit for creating recording pipelines, essentially. Another early application of pipeline architectures are language processors. I'm teaching CS152 programming languages. So this diagram is from there. And this diagram sort of summarizes, it's like the table of contents for CS152. Language processors, the main examples are interpreters and compilers, and they always use a pipeline. So the scanner here is the producer. It reads in your program, your .java file, for example, okay, which as far as the scanner concerned is just a sequence of characters. Okay, and what it does is it lumps those sequences of characters together into what are called tokens. So the output here is a sequence of tokens. The input's a sequence of characters, the output is a sequence of tokens. For example, maybe you have in your program the sequence of characters ELSE, right? And the scanner would recognize, oh, that's the token else, right? And so it converts those 4 characters into the single token else. So we have like a sequence of tokens coming into the parser. And then the parser basically takes those tokens and assembles them into trees. And so we have like a tree kind of thing coming out of here. Type checker goes through each node in the tree and annotates it with a type. What sort of type of value would this expression produce? And then we can go one of 2 ways here. So these trees, annotated trees, go into the translate, and it generates like a sequence of assembly language instructions. Or it goes into the interpreter to this execute. This guy would be a consumer. Maybe the tree represents the expression 2 + 3. Well, the execute is just going to simply execute it to get the answer 5. Pipelines got popular in Unix, so Unix featured them. Again, all of this goes back to the 70s. So a Unix pipeline, so Unix has all of these little programs that you can run. Cat, grep, and sort are examples. Cat, I think, stands for catalog. It's been a long time since I've done Unix. It gets like an input file as an input, and it writes that input file to standard output. It writes it to your console, so you see it, or your shell, you see it printed out in the shell's console window. But instead, here's the pipe symbol. I'm going to take that output, which was normally going to standard output to the console, and I'm going to feed it into the grep program. Grep is like search for a pattern. So you give it a pattern as an input, and it goes through some file, and it generates like a list of all of the strings in that file that match this pattern. Okay, so now it's getting its input from this sequence of strings coming into it, and it's then going to pipe its output into the sort program. The sort program takes a stream and then sorts it, and then this greater than is send it to some output file. And so cat, grep, and sort, they are all running in separate processes in Unix. So Unix had this really easy way of, you have separate, they're all on the same computer, but different processes on the same computer. So a simple way to like form pipelines, just using this little pipe symbol. More modern application are MapReduce architectures. So MapReduce architectures are popular for big data applications, and they're used by platforms like Hadoop. And here you create a tree-like structure of data processors, and each branch in the tree is like a pipeline. I just pulled this picture down from the internet somewhere. So here we have like a kind of a MapReduce architecture. We have like a giant source of data. I'm showing it as a single file here, but it'd really be maybe a dozen files. Okay, and the data from these files are streaming into these map units. Now, what they call map is what is really combination of what I call transformer and tester. So these maps are doing tests of the data. Is this the kind of data I'm interested in? If so, I'm going to transform this data into some sort of format that my user wants. So these guys are all like filtering out what they're interested in and transforming them. And then the reducers here are what I call consumers. So these reducers are getting the transformed data, appropriate transformed data. So this reducer is getting the streams from this first and last map, okay? And they are maybe compiling some statistics or something like that about that and sending it to their output. This guy is interested in different kind of data coming from these mappers, and he's going to transform it into some different kind of statistics, which he sends to output here. So, so each one of these little arrows, paths of arrows, you could think of it as like being a pipeline. So it's kind of like a graph or a tree or acyclic graph of pipelines, made out of pipelines. Okay, coffee break. Client server. So client server architectures started getting popular in the late 80s. So in the late 80s, the 80s, I guess, it depends on where. For me, it was pretty like the mid 80s maybe that I bumped into this. Local area networks. And one of the first questions that we had about local area networks is, well, how do you share files on a local area network? I mean, the network's not going to really do you any good at all if you can't share files. And so they came up with this idea of a file server. Okay, so each node on the network is a client, and one of the nodes is designated as the file server. And so these clients can request files from the server, and the file server, of course, has to deal with all of these issues like the readers and writers problem that you dealt with on your last lab that you did for me. So here we have a couple of clients and servers, and here this client is requesting a service from the server. So clients send requests or queries to servers, servers reply with some sort of response is the terminology I'll use. You can think of, this is the query, what is 2 plus 3? And the server is sending back the response 5. A little bit later on, this client is sending the query, well, what's 6 times 5? And here comes the response back, which is 30. And again, this is a sequence diagram. So this is like time is flowing downward here. Examples of servers, well, everybody knows about web servers, database servers, application servers. So for example, when you do online banking, you are connected to an application server. You can think of the whole model view controller architecture is quite famously used in application servers and distributed applications. The application server is kind of the model. That's where all the application logic goes. The web server is the presentation layer of it. I'm making a little note about that here. Web browsers, database browsers are good examples of clients. If you've ever used Telnet, the client is like a little console window on your program, a shell where you can type in shell commands, but the commands are being executed remotely. The types of requests and responses a server handles are specified by a communication protocol. So you can't just send any request to any server. right? There's certain protocols, like what are the valid requests that you can send? What order do you have to send them in? And so forth. So here are some of the more famous protocols. HTTP, Hypertext Transfer Protocol, that's the one that's used by web servers. So if you're a web browser and you want to talk to a web server, you have to follow this particular protocol. File transfer protocol, post office protocol, there's a simple message, a simple mail transfer protocol, telnet protocol, domain name service protocol. So these are all like defined in the application. If you take a networking class, these are all the protocols in the application layer of the network. Protocols can be stateless or stateful, so I want you to know about this. Stateless protocol, each request sent by a client is, let me put it a different way, the server does not remember the previous request from a client. Okay, so each request from a client is treated as the first request from that client. HTTP, protocol for the web, is famously stateless. So that protocol, basically, clients are sending a request head like to download a web page. And then here comes the web page. Right, and if you imagine that web page is, maybe part of like an online test that you're taking. Maybe the test has 20 questions, and one web page is the first 10 questions, and the second web page is the second 10 questions. Right, so you request the first web page, and you fill that out. Now you request the second web page. Well, the server, the web server, does not remember that, that you already submitted your answers to the first 10 questions. I mean, maybe your answers would affect what will the second 10 questions that I ask you be, right? Like you have this, if you've ever done, like, not that I've ever done this, but, like online traffic school, for example, where, okay, well, I can tell by the first 10, your answers to the first 10 questions, you weren't paying attention. So I'm going to give you different 10 questions that I'm going to ask. Okay, so HTTP famously does not do this. It's famously stateless, right? And that might sound funny to you because some of you might be thinking, well, but there are all of these web apps that are stateful in the sense that, like, for example, the traffic school one, it does remember, what my answers to the first 10 questions were. Okay, well, yes, but the way it does it is through hacks, right? So cookies, or the URL contains in it embedded strings. What were your answers to the first 10 questions? So these are all things that are outside of the HTTP protocol, but are kind of hacky things that are meant to give you the impression that the web server has some memory of who you are and what happened earlier than this. Stateful protocol, on the other hand, allows client and server to have back and forth conversations. So here's an example in a sequence diagram. The client is sending a request to the server, I want you to add something for me. The server says, okay, well, what's the first argument? First argument is 5. Well, what's the second argument? Second argument's 2. Okay, here the answer is 7. So here we have like a back and forth, right? The server clearly knew that it already had argument 1 and now it needed argument 2, for example. Okay, so that's the stateful protocol. Everybody okay? Picture you're all like probably heads down on your tables, sound asleep. No, I'm kidding. I'd like to take a little nap right now. I'm joking. Peer-to-peer architectures. So one of the drawbacks of client-server architectures is that it concentrates all of the traffic and all of the data at these servers. So there's a lot of traffic going in and out of the servers. Servers have to have a lot of memory because they're storing all of the data. So the idea of peer-to-peer is let's make this more egalitarian and more decentralized. For example, in client-server, if a server goes down, that's big trouble. Okay, but peer-to-peer, it's decentralized. So, we've got lots of little servers all around the network. And in fact, it's egalitarian in the sense that a peer sometimes behaves like a server and sometimes behaves like a client. So they have both of these behaviors in them. Okay, here is this is an example of kind of like a BitTorrent is one of the sort of the main protocol that we use for peer-to-peer architectures. So no BitTorrent, it's a file sharing protocol. So we have a network of peers. Okay? Each peer has some pieces of different files. These files might be video files or music files or data files. So nobody necessarily has like the entire file. You might just have pieces of the file. So here's peer one. He's trying to assemble a file. Maybe this is like a video file, like some movie, for example, that I would like to see. Okay, so peer two holds the first part of the movie. So peer one is requesting fragment one from peer two, and here comes fragment one back in the reply. This kind of arrow is a reply arrow. Okay, and then he could start actually playing fragment one for the user at this point. Meanwhile, he's going to request fragment two from peer three. Here comes fragment two back, and so now these can be assembled together. Okay, by requesting fragment two from peer three, peer one implicitly agrees to be a server for fragment two. So here peer two is going, ooh, I want fragment two as well. So he sends a request for fragment two. Well, here comes fragment two, which can now be assembled by peer two. Okay, so it's this. So notice that peer one here is behaving like the client. He's sending out requests, and then later on in time, he's behaving like a server. He's serving up requests. He's responding to requests. Napster, you're probably all too young to remember Napster, but that was like an early music sharing app that used, this P2P technology, the BitTorrent protocol. Bitcoin, let's talk a little bit about Bitcoin. So here peers in Bitcoin are called miners. Each miner maintains a copy of a ledger called a blockchain. So a ledger basically is a bunch of records of Bitcoin transactions. So account 15 deposits 10 Bitcoins into account 35 would be like maybe what a typical transaction would look like. Okay, and so these miners are all receiving, when somebody makes a transaction, okay, I'd like to give somebody 10 Bitcoins. That transaction goes out to all of the miners in the network, okay, and they add that transaction to a block of transactions. When that block fills up, okay, then the miners race each other to try to add that block to the blockchain, make that the official new block of transactions that's being added to the blockchain. And the winner of the race, so everybody has to add his block to their blockchains. That's the official block of transactions to be added. And the winner of the race is awarded with some brand new Bitcoins that didn't exist before. So This is kind of how Bitcoins get minted or mined in Bitcoin. Tor. Tor is the browser that gets used a lot for the dark web. It uses a network of peers called relays that are all relaying parts of requests around the dark web. It's sometimes called, makes it very difficult to trace. So this is like used by like arms dealers, for example, to conduct illegal transactions. But it's also used by I want to say paranoids who don't want people to know about, for whatever reason, don't want people to know about what they are searching for on the web. And then let's talk a bit about, let's go back and think about multi-agent architectures for a minute. So multi-agent architectures are actually the sort of the most sophisticated model of peer-to-peer architectures. Okay, if you think about it, the way we did multi-agent architectures, all of the agents are objects. They're different, they're running in different threads. They're objects inside the same program. So when you're running SimStation, that's one program, and you've got 50 agents. I don't know, maybe they're prisoners, 50 prisoners in there. All of those prisoners are running inside of that one program. But there's no reason why those agents couldn't be running on different computers that are networked together. And that is really sort of the true intent of the multi-agent architecture. And then all of these agents are then peers. The interesting thing about it is that that was originally the concept of Web 2.0. So Web 2.0, Web 1.0 is very oriented toward presentation to humans. So you download a web page, and and then HTML was this like protocol for displaying the web page in a pretty, it was about presentation, oriented towards presentation. So here is like a nice rendering of this web page fit for humans to read. But Web 2.0 was bringing machines into the picture. And so they favored things like languages like XML over HTML, which instead of oriented towards presentation was more oriented towards logic. And and it made it very easy for machines to trade data back and forth, web-based data back and forth, and really like kind of champion like all of the web-based applications that we see today. If you look at the original white papers about Web 2.0, it was agent-based. They talk about agent-based architectures there, where agents are web services that might rely on other web services in order to do the work that they were supposed to do. So really, I go back to everything we said about multi-agent architectures, and that is my sort of official model of peer-to-peer architecture. So you're all already experts on peer-to-peer architectures, where peers are agents and they're sending messages back and forth to each other. So those are the three styles of distributed architectures. I'm going to stop there with the new information, but we are going to come back on Thursday, start talking about your next project, which is Echo, which is a framework for building client-server applications. So anybody who wants to build a client-server application will use your Echo framework to build it. It actually does have a feature in it that allows you to chain together servers into pipeline kind of things. sometimes called, what are they called here? I'm losing it for a second. Proxies, that's the word I'm looking for. So you can chain them together into proxies. So that'll be like our next big project. How are we doing here? Questions? Okay, well, I'm going to go ahead if there are no questions, and I'll end the meeting. Let me just take a quick look here at. Yeah. Okay, so that's it for today. I'm going to have my office hour coming up at around 1:30, but next week we're changing the office hours to Monday, Friday, and then homework is due tomorrow night. So Cycron is, there are a few, all right, I will see you all in office hours then, or on Thursday.